All right. We might as well begin. Thank you again for checking us out. We really appreciate you checking out our videos, our Twitch stream for this series. If you like what we're doing, definitely like and subscribe. Hit that bell notification to be informed of when we drop new videos up on YouTube. We really appreciate it. And we're really enjoying making these videos and definitely plan on making more. So yesterday we were working on more of the test plan documentation. The long-winded, extremely worded test plan, but again, that's what you want. You want to spell everything out to make sure that things are followed and you get accurate results. That's why you want it wordy. You want to make sure your tests are performed accurately, and you want to make sure the results are accurate and you get, your results actually indicate what you're trying to get, what the device is supposed to do. So we were writing the test plan and getting the test log filled out. So now we're starting into the tests where the board is powered up. And this is where we're going to have to make some decisions on what more we want to test, how close to potentially destructive tests we want to be for our first board. So again, for our first board, we're going to want to do, this is basically the pilot board. I want to ensure that it at least has some basic functionality and that the core design is working before we do anything that could potentially be destructive. That way, it would basically greenlight the ability to build a couple more boards for potentially destructive tests, such as loading up the power supplies and actually checking the ripple. So, like, I pulled up the data sheet for the buck regulator chips, and so it shows their output ripple, but while it's loaded, 2 amp load. So we will want to load these power supplies up and kind of see what they can do. Make 2 amps, push them to their limit, and that could be destructive. Because not only will we want to load them up to 2 amps to make sure they operate as they say they do and properly and safely without damage, we'll want to check the ripple, and we'll also want to check the thermal characteristics, make sure they're not going to get too hot if they ever have to deliver the full load. To be fair and honest about this, with this board, the facts of the matter are the 3.3 volt. You're not going to be delivering that with what we're powering by that. The most power consumption, the biggest power consumer is going to be ESP32, especially if we're using Bluetooth or Wi-Fi with it. That's going to be the biggest power consumer of it all. The RS45, the limit switches and control inputs through the optos, those aren't really huge power consumers. They're more like just voltage sensing, so you're not really drawing much current. You're talking in the microamps. We're at the very most low milliamps. The USB UART will be drawing a little bit of power, but not a lot, because it's only going to be active when we're actually programming it from the outside, through the ESP IDF or through VS Code with the extension installed. The UART here will consume a little bit, but again, that's still tied to the ESP32, and that's only going to be during debug sessions. And the stepper driver, the chip itself, as far as the logic, really doesn't consume much. It's basically detecting voltage levels on these control inputs. And the real power that drives the motor, it's straight from the 24 volt source. It's not even being fed from either of the power supplies. So our actual expected use power consumption is we're probably only looking at most 750 milliamps. Nowhere near what these switching power supplies are capable of delivering. But that still means but we still want to push them and test them just to validate they do operate at their rated values. So we will do a loaded test, but since that could be potentially destructive, we'll wait to do the ripple, check the ripple, check the thermal characteristics at fully loaded. But for now, we want to basically test the basic operation of the board, again, to validate that the design is good, and basically green light us to build a couple additional that we could destroy. So let's shelve the ripple and the loading and all that for now, because the next real tests are some of the other components, such as the RS-45. So what this is going to need is, so here, so the test plan, now that's going to be part of the functional requirements and stuff, so I have to revisit all of that. So let's go pull up the original matrix that, like I said, I had ChatGPT write. And again, it's kind of like in a format that I'm not really too happy with, and kind of written in a weird way. The test IDs we're going to rewrite because the matrix will match the test plan, but technically the traceability matrix is duplicating what's going to be in the test plan, but it kind of spells it out in a more more convoluted way. So maybe we won't even worry about traceability matrix. We almost don't need it since we actually have a test plan and a test log. So that'll force us to kind of rewrite the product requirements document. Because that's what that matrix is supposed to do. It's supposed to tie in your product requirements, it's just a PRD. So the PRD, so it's to tie in what you define as the requirements. It's supposed to create a matrix of all these requirements, tie them into a matrix. Then that links them to the actual tests and stuff. It's a really confusing and convoluted way of doing things. It's not as straightforward as it should be. So I think what we'll do is we'll get rid of the traceability matrix, and we will go and tie everything in through the test plan itself and the test log. So the test numbers here. So what we'll do is, we'll kind of unconvolute it and get rid of that traceability matrix. I don't really like that. It's just too much extra duplication, replication of stuff. We don't need it. Let's simplify our processes. So we're going to look at the functional requirements here. So now, do we have to actually test for this? So these are functional requirements. Basically, these would just be a checklist. Does it meet all these? Yes, it does. I mean, it meets these. So I have to verify the motor current here. Provisioning time, again, we're gonna kind of clean all this up. We're gonna use this as a guide. So functional requirements, these are pretty much just checklists. And technically, so that's initial assembly testing. So then what we can do then, let's kind of see. Yeah, I don't like this. Okay. So let's give ourselves a little bit more room, because it's much easier to delete rows than to add rows. All right. So what we're going to do then is, so that's the assembly testing. So what we're going to do is come up here. Merge cells. We're going to center them. We'll break that into a section. So we're just kind of turn this into a checklist based off of this. Functional requirements check off. Let's just do that. Checklist. So what we're going to do this is kind of merge cells. Actually, what we can do then is to simplify our lives, copy this. Kind of see what we can do here. Test item. Requirement identifier. Requirement. Result. Help device build rate. And notes. All right. Okay. So let's kind of simplify our lives a little bit. So it's going to be FR001 through 7. Well, let's see here. FR001. So basically, I'm going to drag this off the screen to just make it a little easier to put it in the matrix. That way I'm not flipping screens, flipping pages too often. So FR functional requirement 001. And then quite simply, basically what it is. Does the design meet that requirement? And it'd be pass or fail. So can I drag this down and we'll, yes. Does our design meet? Yeah, much better. This makes more sense than that trying to tie everything in with that matrix. 1224. So we're just going to, yes, it can handle 12 volts. And there are, I guess it would be fine to work with 12 volt systems. This would still perfectly operate. The stepper driver will operate with a 12 volt, if I'm not mistaken, input. So we can actually find out and validate. Let's not make any assumptions here. DRV 8825. PWPR is what we're using. Let's double check. Let's make sure. Yeah, the minimum voltage is 8.2 volts. So yeah, the maximum volt is fine. So yeah. It'll handle 12 volts. So if you have a system you want to work with 12 volts, is perfectly fine. And we'll make sure any documentation that is to support it for sales or whatever actually mentions that. So that's perfectly fine. So Pluggable headers. Yes, we do have pluggable headers. All right. Functional requirement 5. Again, that's the beauty of working with your own systems. See, the great thing about ISO, it just tells you, or other QMS systems, I'm just going to keep referring to as ISO, even though I think there's many other systems out there for quality management systems. It just tells you that you need to meet these requirements. It doesn't tell you how you have to meet these requirements. So if you want to design, kind of come up with your own system, as long as it meets those requirements, it doesn't matter what your system is. So this is one thing I failed on, but it's kind of fine. We'll rewrite it for now. Right, functional requirement 06. Because these things we really can't test on. The only test you can do with things like this are visual identification. So it almost okay. Yeah, there's no way to test it other than to visually confirm that it's there as part of ours. So performance requirements, these are things we can test. So I'll kind of bring this back over here. So performance things we can actually test. We can throw an OTA over the air firmware on here and test it to verify. If we really want to, like voltage regulation ripple, we're already kind of testing that. And so what we might want to do is instead of making it one of these type of tests, we can write it because these are generic tests that we haven't outlined in here. What we can do then is kind of go here. Let's get rid of these guys. All right, let's copy that. We'll come down a couple cells, paste those in there. Let's copy this guy, paste this guy in here. What we're going to do is we're going to call that performance requirements. Helps if I would spell. See, can I spell check this in here? Yes, I can. I love it. All right, performance requirements. So then, copy this, paste into there, and boom. So what this will allow us to do is to kind of merge these together to get things to match properly, the test plan, without that stupid traceability matrix, which we're going to get rid of. So PR 001, we'll rewrite this as we need to. So we'll leave these in here because we might have to write some BLE provisioning stuff. So mind you, these will probably be their own firmware that we'll have to kind of develop and get functional. So, and test basically as individual modules before we work on tying everything together. So some of them are board level actual hardware, and some of them are basically hardware slash firmware. Because temperature rise, we'll probably want to do that. That could be considered maybe a destructive test, because we'll basically want to load the power supply chips up, and we'll want to load up the stepper driver, have it driving a motor, maybe under a load or something. So we might have to figure out a load. May have to build a mechanical load for it, because motors and things perform differently based on what's going on. So you'll have an unloaded mechanical motion and a loaded. So when it's loaded, the motor is obviously going to pull more current. So we're going to have to do some stuff. So, yeah. So we'll kind of keep that stuff in. Again, I'm going to drag this off to make it a lot easier for me. That way I don't have to. That's why I like multiple monitors. 0, 1. And it goes down to 5. We can always expand on this later. Motor current output. Let's make sure. I'm going to check the data sheet again real quick for that guy. So it does say it can handle up to 2.5 amps. So we might actually have to, we could actually test it unloaded by having it to pretend to drive loading resistors. We have the voltage. We know the current we're trying to pull out of it. So it's just a matter of figuring out the resistance. I may have to find some power resistors that can handle the power output. I've got a couple, but I don't think they can handle the wattage at that kind of... so let me grab my calculator and do the math here just to get an idea here. So using Ohm's law, so the power, basically the wattage, we're at 24 volts, and it's times 2.5. So we're going to need resistors that can handle 60 watts of heat, of power. And I don't think the ones I have on hand. So I'm going to have to look on Amazon or something to see if I can find some power resistors that can handle at least 60 watts. I don't want them frying or damage anything. I may have to build like a little test fixture or something. So again, but it's tests worth doing. Up to 2.5 amp loaded. Make sure it's you clarify it's loaded. BLE provisioning time. Again, that we'll have to figure it. BLE provisioning time. Seconds. All right. So ambient. Yay. I mean, it's kind of good because even though we may not use this in our firmware or down the road, it's still kind of a good idea to make sure it can actually accomplish these. And voltage ripple. Less than millivolts. Okay, so we have our performance requirements. Like I said, Copilot helped write these. We might expand on that later. So then we'll have to figure out our test plan where that goes. Now the great thing is so I'm going to come back over here. I'm going to drag this off screen so I can refer back to it a little easier. So then what we're going to do is come to our test plan. Test plan. Functional requirements. Functional requirements. So technically, that should be above this. We're going to come up here. All the way top. Okay. These tests are only. Actually, let's get rid of that. Let's kind of do. Performed during the inspection of our -01. And verify spreadsheet. Does the design include an ESP32 with and BLE? Seriously, that is the test. But you know, it was written into our product requirements document. We need to verify it. 02. Does the design include the DRV 825? I don't know why I capitalize some of this stuff. I see with step and two. So one of the things we'll have to do down the road is also kind of print out the schematics into a PDF to kind of go with this. You know, that could be part of. So one of the things we're going to do is put together like a packet. And here's another thing I'm going to kind of show you. I'm kind of crazy like this, but this is how I like to organize. And oops, wrong thing. I'll just kind of show you what I'm doing, what I'm planning. I think this is what it's called. There we are. So again, I picked up one of these guys for myself. Again, I'm not endorsing telling you to buy this or follow what I'm doing. But I'm going to be using things like this type of device to put together like packets. Like you know, so technically with a QMS system, anything printed would be considered uncontrolled. So I want to try to state that in headers and or mainly footers with things. So we might have to go through and kind of add some text to the schematics. Won't really be a revision. It's just, you know, technically adding text. We're not really changing the design, so I'm not going to count it as a revision. I'll just kind of put it down here by the title block. We'll get to that, but it'll technically be an uncontrolled document when it's printed. And then I'll make, little, like a packet that'll have all this stuff together in an easy to use, easy to digest format. And that can stay physically. The test log will then, remain digital, because there's also something else in the industry that down the road we'll worry about. This for now, it's nothing that we need to worry about, but when we hit to the point where we're at production, so we'll run through these tests again. I mean, every iteration, if we have to spin this board again, the tests get run. So if we make a design change, update the PCB, add or remove components, or change anything, we still will be running through the test plan. Basically consider a first article, because it technically is. And with any changes, like if, we'll have to review it, if there's like parts added, parts removed, if we decide down the road we want to add the proper test points for these guys, we will. And it'll be reflected in the test plan, and test instructions will be properly written for that, and updated accordingly. But at the end of the day, when we're at the point of release and we've done this, we'll set aside what's called what the industry refers to as a golden unit. So basically, we will take our first board that it looks 100% proper, tests 100% proper. That basically, instead of shipping it, what we'll do is we'll actually seal it up with printed copies of like the final test plan for it, like the final test results. We will print it up in a moisture barrier and seal it in a moisture barrier bag and mark it as like a golden unit. So this is like, that will become our de facto golden unit that we're shipping out the door. That will basically become our point of reference, the board that we are saying, yes, this is our production scale board, and it'll just be stored and held on to for a while. Probably retained for a couple of years. It's called the golden unit. I don't know if it's really a practice done too much nowadays, but it's something that helps, because you can always refer to the documentation in this board when all else fails. This is the unit that all your testing was done on. It performed exactly as you needed it to. And, so it'll be stored, have desiccant in a moisture barrier bag with a copy of the printed test results, the test log. That way you can always refer to it, no matter what, your golden unit. So, but that's down the road. That's nothing we have to worry about right now. So, okay, so we'd have to print out the schematics. Maybe we will actually call out the schematics here. Okay, well, we call it out up here, so that's fine. FR02. Three. Support port 12 to 24 volt DC. Input with logic circuits. Again, just the verification. We say we want it as a requirement for the design, so we need to verify it. LSP design incorporate for 45 control. I don't know why I do that. inputs. And order outputs. Make sure the wording matches in there. So yeah, it does it. Okay. It's USB phase 432. Realistically, it doesn't matter if it's, you know, any of the standards. You know, you could even use A if you really wanted to, but we just chose C. It's going to have a USB interface. Incorporate for the files. Right. Yes, for so technically we do. We have the two on the power rails and the one status LED that can effectively be programmed for anything you want it to be. You can use it as a heartbeat. You can use it as a status indicator that flashes based on failure mode, which we could do. We could design some kind of failure indicator and have different flashes for different failure conditions. Like if a failure condition is like, you know, the stepper motor driver presented a fault and we picked up on it, we can flash for that. So there's a bunch of different things we can do. And there we go. I think the should incorporate the spelling of the alternative to into the English language. That way it doesn't matter. That way we can all make the same mistake and not have to worry about it. So those are functional requirements that we spelled out, and technically they're just verification only. I mean, there's no other way to test it other than look at it, make sure, you know, compare the design. Does the board actually have it? Boom, problem solved. So we have our initial testing. We're going to break this down here. So I'm going to go here. Nope. I'm going to call this initial PCB testing. So we have initial resistance measurements, blah, blah, blah. And then the initial board power up testing of the low voltage, and then the actual operational voltage. So we have that. So let's go to our save, go to our test plan. Safety and regulatory requirements, verification and validation plan. We'll have to work on that. A safety checklist, bench test. Let's see here. Okay. So, all right. So, validation plan. All right. So this kind of outlines the stuff that we're going to be doing. So what I can do then is let's change this verification and validation plan. What we're going to do then is just refer to document P1022025001 dash test plan.md. Let's do this for detailed detailed breakdown for detailed test plan to meet details plan to the outlined requirements. There we go. That way we're not duplicating our work. So again, we're probably going to be expanding on some of this stuff. We may want to, as we go, and come up with other testing while we're kind of doing some testing. Which is kind of funny because there's some things we're going to want to test. So these are just requirements we outlined. But we're going to want to do some other testing. All right, so safety and regulatory requirements. So one of the things we can test for, so we can actually test for reverse polarity protection, which could be destructive testing, which we'll do later down the road. Because I don't want to destroy this guy. Now this is just the requirements. These are just requirements that are outlined, so I think we're going to move on from them for now, because there's other testing we need to do. So we've got the board powered up. We're not going to do anything that could load it, could damage the board until we're ready to say, hey, yeah, it works. So at this point, so let's go look at our schematic. I'll leave that open. So another thing I want to clarify before I forget. So like I said, I created a generic thing for a company logo just to use it as an example. And I'm just going to be that guy. I don't want the Magic Forge logo just out there that anybody can use it willy-nilly and claim that they made products for us. I've seen it happen, and other projects, and they put their logo out there too easily, made it too easy, and then all of a sudden you got all these copycats saying that they're making products for you, or they were authorized by you to make under their name, basically licensed. I just want to put that out there. I believe in what I'm doing, what we're doing, and I just don't want to risk it. So what I'm going to do is, once we get to the point where we're ready to release the sport, after it's gone through all the spins, I'm going to keep all this together. We're going to keep doing it all together here. But when it's ready for release, what I'm going to do is I'm going to basically freeze all changes with the public, with the documents and everything I'm sharing. And that'll be the end of that part of the series. That phase of the series where the design, the development, the ready for release comes in. And I'm going to kind of splinter it off to a project that's going to be controlled and managed by the Magic Forge. I'm going to replace this logo with our logo, and actually, push these products out there under the Magic Forge branding for the ones I'm selling. Again, it's going to be an open, it's an open project. If you want to build these and do whatever you want with them, that's fine. The firmware is going to be very generic that they're shipped with. It's going to be very basic testing firmware. The documentation outline that. It's basically, you come in, you figure out what you want to do with it, and you make it do what you want to do with it. So if you want to put this in a project somewhere, that'll be up to you, whatever you want to do with it. that's the whole idea behind this being a dev kit, basically, for the stepper motors. But yeah, for final release, it's gonna, if I'm gonna be building these and selling them, they're gonna be under the Magic Forge branding, through our Amazon shop and maybe Shopify down the road. I might get that going again, because we have the Magic Forge domain, and we did have it linked to a Shopify account. We were trying to sell a few things. We kind of broke away from that. We kind of changed our direction a little bit, and now we're going this way, kind of revitalizing it in different ways, different ideas, different concepts. But that's the way business goes. You always got to be willing to change your course and your path if things don't look like they're going that well. Sometimes holding on to something isn't worth the effort. Sometimes you're better off just changing and adapting to the conditions in which you really like to do. So I just want to let you know that, this is generic. So, personally, at the end of the day, this is going to be an open project. The file's already out there. Some overseas company is probably, they can take it, slap their name on it, and sell it as theirs. You're going to have that. You're not going to stop that. You're not going to stop that theft. And even the general firmware that we finally developed for testing stuff, will eventually be out there. But it's going to be stuff you can already do with the ESP32, with the IDF. It's not going to be anything fancy. All the firmware we're going to develop is stuff that you can already do. It's nothing special. But I'll have the individual test modules that will eventually be incorporated into one big module, to one big firmware suite that's going to go with this unit shipped. Because we're going to have a module for controlling the fan, reading the temperature sensor, and controlling the fan. Figuring out set points for that we'll have to do down the road. Module for reading the input, the control inputs, and the limit switch inputs, because we'll want those to be interruptibles. So we'll want to definitely have those as a separate task that can interrupt the primary task. The UART, the debug interface, I don't think I'm going to really care if it's interruptible. It'll be a separate task, but it'll just be a basic serial UART where you can kind of control things and read things. And then the stepper motor, the RS-45 may be interruptible. That way, if, maybe not. It's going to be really dependent on what you want to do with it. Because if you want to use it for like DeviceNet or something, or one of those type of net interfaces, you might want to be able to interrupt the ESP32 for sending, getting status and commands and stuff. If you want to do like DeviceNet or one of those type of things, the stepper driver will probably be on its own task. That way you can send inputs and controls to it. So we'll see. And then what's cool too is the boot button can be used for other purposes within the ESP32. So we already have a button that's assigned to a pin, and down the road, so it's only used during the bootstrapping phase, to put in a bootloader mode. But once you're actually booted up, once the system's actually booted up, you can actually use that pin for other things. So we can even use that as a button to enable like OTA updates. So that's something you can do with it. I'll make sure we can do some testing with that and put that in the documentation as well. So that's where we are with it. I just want to kind of let you know what was on my mind, our plans moving forward. But for now, this generic logo is going to stay here. That way our Magic Forge logo that will be working doesn't just get out in the wild that easily. You have to actually work for it if you want to throw it on here. Because, the logo's already out there in some way, shape, or form with our YouTube page and all that. So back to the planning. So based on the schematics, things we need to test. So we basically got those tests, ESP32. So let's start here. So let's say we want to do some basic UART functionality tests. Let's start there. Let's kind of grab. It's just easier for me to Yeah, copy and paste. Oh yeah, I forgot that I could do that in here. Oh yeah. Oh, it just expands it the minute I hit the enter key anyway. So we're going to do sub technically we'll just call them subsystems. Subsystem. So subsystem testing and verification. So that'll be all the little subsystems like the UART, the RS-45 UART, the fan system, the temperature system. You know, we'll be testing all those individual little subsystems. So what we're going to do is we're going to just kind of copy a few down here. We're going to paste it here. Clean all that up here. Word for word, we're just going to copy that. Paste. I hate that. Okay. Okay. So I'm going to, let's figure out what we want to, you know what? Let's just, SST1. Subsystem test 1. Again, it's our system. We can name it whatever we want. Subsystem test 1. All right. Actually, one of the things we need to test first is not the UART. I'm glad I got it. Didn't get ahead of myself. We need to verify the USB UART we can actually connect and program the ESP32. That's one of the first subsystem tests we need to verify. Okay. So, let's go up to the top. I wish that would keep those closed. Required materials. Let's see. Here, system with USB and software to ESP32. Appropriate USB cable with power and data to the assembly. Appropriate USB-C. Because we built this with the USB-C connector, we're going to make sure we spell out we need USB cable with power and data. Because remember, the UART chip requires reading from the V-bus. It basically does a voltage check to make sure that you have power coming in from the V-bus. It needs that to know that you're actually connected. That's how it connects. So let's go here, appropriate USB cable. Okay, with the assembly power supply set at 24 volt DC and enabled. Um, assembly. Does the system recognize a newly recognize a port? So that's the first thing that we need to do is connect it, and your computer system should recognize a newly added serial port. Now I will remind you or inform you that these brand new USB-C connectors, after they've been reflowed and soldered and everything, they're assembled to the board. Sometimes they're a little bit tricky. They're a little tight. So sometimes you have to connect and disconnect the USB cable a couple of times for them to work. That's just something I've run into. So just be mindful of that. So we'll go back here, SST. Does the newly connected so does it recognize the serial port? That's the first thing. So that'll tell you right there that the UART chip is active. That it says, hey, I see a USB connection. I see your cable connected. I'm alive. And then it also says your computer will say, hey, I see a serial port. I see a COM port that I can communicate with. Now, again, there is no firmware at all on the chip. So we have to figure out what we want to do. Do we want to throw in a more complicated test, or do we just want to do test after test after test after test? So one of the things we're going to need here, terminal runner on PC. Serial cases. We're going to need a USB to UART. And RS-232. Assembly. Helps if I spell that properly. So that's something we're going to need, because we're going to need that to communicate to the ESP32 via this guy right here. We'll get to that later, but might as well throw that up here. So we need terminator. I think it's PUTTY. Would be putty. So we'll be using putty, obviously, to do this. So we'll need that. But I think for the first actual tests is we're just going to throw together a basically a hello world that basically just reflects back on the USB port. It's just going to just do a print statement to the USB port, to its serial interface, and you should be able to read it through the IDF. See, this is where things are going to get a little bit more complicated, because we're going to need to kind of develop the firmware. We're going to have to kind of give them names and stuff. And we're going to have to do some funky kung fu and VS Code. That way we can have basically separate tests. So what we might do is, let's go back to our folder structure here. Project, stepper controller, firmware. What we might have to do is break this out to a bunch of different individual folders. So we're going to call this basic testing. So sometimes it does not like spaces in names, so we're going to call it basic modules. And then that's where we're going to kind of come in here, create individual modules. So we're going to call it the good old-fashioned Hello World. So then we're going to just kind of get in there and throw firmware together. So for some of this stuff, we might be able to kind of early develop and get ahead of this and use a regular ESP32 dev kit and kind of write some of this now, like the Hello World, and just throw it on there and kind of get started in creating some of the test code. Yes, this is a bunch of jumping through hoops, but unfortunately that's the way the game is played. This way you can isolate and test specific modules one at a time without code interfering with other modules. And then once you validate each individual subsystem, then you start mixing your different systems together in all your integration, your firmware integration. But for initial product testing, you want to isolate and have just one module at a time. So for this, the whole idea of this whole Hello World is, one, to test that you can actually program the device, that the auto programming works, and that USB serial port actually, you are getting data back and forth. That's what it is. Now, another thing I've run into is sometimes fresh ESP32s that have not been flashed at all are stubborn and do not like being programmed the first time using auto program. It's really weird. They get really bizarre. And sometimes you have to use the boot and enable buttons and actually force it into firmware mode and then program. They do some weird stuff. Fresh ESP32s can act pretty weird, and I've seen it too many times. So it might be frustrating. We may have to write that into here, but for now, we'll just kind of like leave it basic. Using the computer and ESP32 software, load up the initial Hello World and validate that the system can program the ESP32 and that basic does over the UART interface. So that's what we'll do. And then the test log, SST2, does the basic world firmware program and function properly. Okay. So that tests, that just tests the UART. Now, one of the things we can do is, if we really wanted to, sometimes you may want to spell out exactly why you're testing the system. So here, this states that the USB to chip is UART. Okay. And that The computer does detect port. So you can spell it out this, and maybe we will do it to not fluff it out, but to kind of explain why why we're doing this test. Some of the tests are more self-explanatory. Some of them are not. This test validates that the ESP32 can be programmed, boots, and operates normally. So we can do that, kind of expand on why we're doing the tests. So those I think should have been the very first subsystem testing, because obviously without being able to program the ESP32, all other testing will be pointless. Let's kind of go here. May need to use the boot and enable. Is it enable or reset? Let's make sure we're using the right term. Boot and enable buttons on the PCB. First program upload for the first ESP32 flash. Again, these devices can be fidgety. They can be finicky at first. But usually once you get them flashed the first time and they'll boot and they'll operate, usually they have no problem with the auto programming. It's just, I've seen them act really weird, every once in a while, especially when the brand's making new out of the box. It's really weird out of the tape, I should say. So that'll be that test. So we have to do that. So again, we'll have to develop that firmware. So maybe next time what we'll do is I'll grab one of my ESP32 dev kits, and before we roll too far along, we'll start kind of sussing out the structure, start the firmware foundations to get things started. Yes, there'll be a lot of stuff. I'm gonna have to do a lot of get ignores, so I'm not pushing all this extra junk up to GitHub. I know I'm gonna have to do that, but that's fine. It's just a necessary part of the process. Again, you want to keep everything separate modules while you're testing individual subsystems, and we've got how many individual subsystems? So this is one of them. Basically, test that. We need to test the standard FTDI UART. We need to test the RS-45 UART. We'll have one to test the limit switch inputs. And we'll have one to test the control inputs. And then we'll have one to basically test the fan, test the temperature sensor, and also then test the stepper motor. So I didn't even bother counting, but on this sheet, there's going to be 3 separate subsystems. So 3, we'll count that. That's 4, 5, 6, 7, 8. So a total of 8 subsystems. 9 if we want to count the status LED, which we might just count that, just kind of throw that in there because that is a subsystem. If we want to test the Wi-Fi and BLE, we could be looking at 12 or more subsystem tests, depending on what we really want to do. But right now we're looking at just a hardware. So we're looking at like around 9 individual hardware subsystem tests. So that's firmware we're going to develop for each one of them individually. Some will be very simple, like this guy. We'll just flash them, have them blink at a set interval just to make sure it works. This will be a basic UART serial interface. We'll write one that basically will mimic the UART interface. With the RS-45, it'll just be for the RS-45 chip, and we'll be using that adapter. Let me make sure that's actually in here. Oh, nope, that's not in here. USB to RS485 adapter. And two wire for interfacing. The 5 units for interfacing to RS485. Okay, so lengths of wire. I've got a little cable, little three conductor cable that I can use. Ain't no big deal as long as we got 2 for the A and the B, and we know which is which. We can identify them. So we need to make sure we have that. Small lengths. We'll just get short. 2. Actually, 1 foot lengths of wire, because you don't want RS45 to be too short. I think a foot should be a good enough minimum. We can go a little bit longer. You know what? And 2, we'll just do 3 foot lengths. Why not? Let's make sure we have enough wire there, enough of a length that there's no problem. That shouldn't be a problem. So we'll do that. We'll need that to test that. Test this guy. And we'll run the same tests, the same firmware, terminated and unterminated, just see the results. The great thing about RS45 is either the data will get there or won't. I mean, it'll be corrupted. So, you have kind of 2 failure conditions. You either won't get the data or it'll be corrupted, and you'll notice that right away, because it's just going to be kind of like basically take data in and spit something back out to you. That's what we're going to do. We'll rate the tests for that. They'll be basic tests. We'll just tell them, hey, process the data coming in and spit out this data and return to, this keyword or whatever. Very basic tests just to make sure we can send and receive data on these UARTs. But the great thing about them is either they're going to fail and you're not going to get data, it's going to be corrupt, it's going to be gibberish coming out. So we'll work on that. The limit switches, we're basically just going to be that with the LED, the status LED, if limit 1 is kicked, flash it once. If 2 is kicked, flash it twice in succession. If 3 is kicked, flash it 3 times. We'll do things like that. And then, for the fan, that's easy. We'll just basically apply PWM to it and read the TAC and, see what we're getting off the fan, the temperature sensor. We can use, like I said, we can tape a thermocouple next to it, kind of get a reading, kind of see how similar they are, because we'll have to make sure we can write in code that can convert the data over that it's reading, make sure it's converted appropriately, take a heat gun, kind of warm it up a little bit, kind of see what happens, things like that. So those kind of tests we're going to have to write. And then we'll start incorporating all of it into some more unified testing, the motor kind of, does it turn? Can we make it go forward? Can we make it go backwards? Basic testing like that. So a lot to write, a lot of firmware development to fit this test plan and the results log. But we'll get there. One step at a time. That's all we can do it, piece by piece. So I'm going to end it here. We're a little bit over an hour. I thank you for checking us out, for following along. I thank you for checking us out on the Twitch stream. This has been a lot of fun so far, and I want to keep going with it. So have a good rest of your afternoon, and tomorrow's Monday. So be streaming and recording the next video in this series tomorrow around 6 p.m. So thanks. Have a good day.